When a substituent contains branching within the substituent, we actually think about naming the substituent much like we'd think about naming the parent compound with a branch or with a substituent contained within it, typically thinking about the attachment point of the substituent to the parent chain as carbon number 1 in terms of numbering the carbons. And so two-step process for naming substituents that contain internal branching. First of all, we're going to identify a parent chain within the substituent, the longest linear chain of carbons within that substituent. And typically this won't be more than 3 to 4 carbons. When you get that long, that long chain of carbons typically starts becoming part of the parent chain. And we're going to number it starting at the point where that chain attaches to the parent, the sort of main chain of the compound as a whole. Once we've done that, we're going to look for branching points and substituents connected at those branching points. And we're going to add the names of those substituents as well as a locant number to indicate where that substituent is located. All this said, it's quite common for small branch substituents to have common names, and we'll review those as well on this slide. So let's go through this process with these examples that we see on the slide. So first here, we have a 3-carbon substituent, and the longest linear chain of carbons in here includes 2 carbons, and we're going to number them starting at this carbon, which is the one that is attached to the rest of the molecule, the parent chain. We see a substituent at carbon 1. That substituent is a methyl substituent, and so we name the entire branched group 1-methyl ethyl. It's got an ethyl parent chain with a methyl group at carbon 1. 1-methyl ethyl. Now this is much, much more commonly called isopropyl, and I believe according to the IUPAC conventions, and as far as I'm concerned, this is fine. Calling this substituent isopropyl in any and all circumstances is completely okay, provided it is a substituent and not actually part of the parent chain. Down below, we've got some 4-carbon substituents. In the first case, we can see that we have a 3-carbon linear chain, so it's a propyl chain with a branch at carbon 1. So we number with carbon 1 as that point attached to the parent chain. There's a methyl group linked to carbon 1. This is 1-methyl propyl, much more commonly called the sec-butyl group, because this carbon we can think of as secondary. It's a secondary carbon attached to the parent chain. In the second case, now that methyl substituent is not linked to carbon 1, but carbon 2. So this is now not 1-methyl propyl, but 2-methyl propyl with a methyl group linked to carbon 2 there. It's much more commonly called isobutyl, and one thing you can notice about isobutyl is it resembles the isopropyl group. It looks kind of like an exploded isopropyl group with an isopropyl group linked to a CH2, which is in turn linked to the parent chain. Finally, we can have 3 methyl groups linked to a single carbon as a substituent. This has a 2-carbon parent chain within the substituent, 1, 2, and there are 2 methyl groups linked to carbon 1. So we call this a 1,1-dimethyl ethyl substituent systematically, although it's much, much more commonly called the tert-butyl group. And we call it tert-butyl because this carbon with 3 methyl groups attached to it can be thought of as tertiary, a tertiary carbon connected to the parent chain. Now that we know how to name the parent chain and the substituents, we put it all together to assemble the systematic name. And to do this, we identify that parent chain and we number the parent chain. If we end up with 2 chains of equal length, we choose the parent chain with the greater number of substituents by convention. We then identify and name the substituents, number the parent chain, giving a locant number to each substituent, and then we arrange those substituents alphabetically. A couple of extra quirks here that we're going to dig into on this slide. We start with numbering the parent chain, giving the substituents collectively the lowest numbers possible. This generally means you want to start numbering from the carbon closest to the first substituent. So here, for example, what's correct in this case is to start numbering relatively close to the methyl substituent. You do have to start on one end or the other. It's incorrect to start on the other end of the molecule, which is farther away from these 2 methyl substituents, and you'll notice that the overall numbers are lower in the correct case, 255 versus 336, in which case the numbers are generally higher. If we've got multiple copies of the same substituent, we use the Greek prefixes di, tri, tetra, penta, etc. to group all of those substituents together. This is true even when those substituents appear at different carbons. So for example, here we would think of this trimethyl compound as 2,5,5-trimethyl. That's how we would name all three of those methyl substituents. Keeps things more compact and shorter, right? There's no need to separate out the 2,5,5 methyl, the methyl groups at carbon 5 from the methyl group at carbon 2. We can just call it 2,5,5-trimethyl heptane in this case. So again, the overall process, we're going to identify that parent chain, the longest contiguous chain of carbons. We're going to identify and name the substituents, number the parent chain, and assign a locant to each substituent, and then arrange those substituents alphabetically prior to the name of the parent alkane, the so-called root or base name. Let's practice generating systematic names for acyclic alkanes. Now, providing a systematic name for each of the following compounds. All right, so first and foremost, we're going to try to identify the parent chain. This is the longest contiguous chain of carbon atoms. In this first case, we can notice, for example, that I've got a pretty long road running sort of from the bottom left to the top right of the molecule. If we count the carbons in this chain, I've got 1, 2, 3, 4, 5, 6, 7, 8. And it is worth verifying that this is in fact the longest contiguous chain of carbons in this molecule. This makes this compound an octane. Octane is the base name, and we're going to number the carbons to give the substituents the lowest numbers possible. This is a little bit tricky here. We want to avoid starting numbering over here. We'll notice that we go 1, 2, 3, 4, 5 to hit this methyl substituent. But if I start numbering from the other side, I go 1, 2, 3, hit the first methyl substituent, and 4, hit the second. So the numbers are lower overall if I start numbering on the left. So that's why I'm going to start numbering at the bottom left, carbon 1, up to the top right, carbon 8. Now we're going to identify and name the substituents. In this case, we've got CH3 groups, here, here, and here, branching off of the parent chain, and those are called methyl groups. We've got 3 of them at the positions indicated, and those positions are carbon 3, carbon 4, and carbon 6. And so we can assemble the substituents into the prefix name 3,4,6-trimethyl, where the tri comes from the fact that we have 3 methyl substituents in the structure. And this is the name, 3,4,6-trimethyl octane. All one word, no spaces. There you go. All right, the case below is pretty interesting looking. It looks like we have something like 3 isopropyl groups connected to a central carbon. So as a common name, someone might call this triisopropyl methane, right? Thinking about CH4 with 3 isopropyl substituents. But that's not the systematic name. To do the systematic name, we need to find that longest contiguous chain of carbons. And in this case, it's going to be, there are actually multiple ways to think about the longest contiguous chain here that end up being equivalent. They all have 5 carbons, and they all be numbered the same way as well. So if you didn't quite see it this way, that's okay. For example, it's equally correct to think about this W-looking chain as the parent chain. You'd come to the same name, and this is worth verifying on your own. All right, so we've got a pentane, that's 5 carbons, and we're going to number it like so. Here again, the molecule's actually symmetric, so it doesn't matter which carbon you start on. You get the same locant numbers in any case. Now we're going to look at the substituents. I see 2 methyl groups, and I see a 3-carbon substituent here, which is the isopropyl group. That's the common name. We could also call it 1-methyl ethyl, since it's an ethyl substituent with a methyl group linked to carbon 1, but isopropyl is more common and completely fine. We've also got 2 methyl groups. The methyl groups are located at carbons 2 and 4, and the isopropyl group at carbon 3. Now, in assembling these different types of substituents, we're going to put the isopropyl group first, because alphabetically iso comes before methyl. And confusingly, this di prefix actually doesn't figure into that alphabetization. This is a convention. It's not super important to remember, to be perfectly honest, but the alphabetization is based on the M here and the iso here. And so we have 3 isopropyl, 2,4-dimethyl pentane is the name of this compound.